Now that we've looked at the basic type of double replacement in precipitation reactions and understand the solubility rules required to figure out whether the products are aqueous or solid in a typical precipitation reaction, we want to look at the ways in which we can write out precipitation reactions to give someone reading our equations a very good understanding of exactly what's happening in the reaction. This is a process known as writing net ionic equations because of the fact that in an ionic substance, when it goes into water and becomes aqueous, it dissociates into its anion and cation, and we need to be able to reflect that in our balanced equations. So let's say we wanted to write the equation for lead-2 nitrate and potassium iodide reacting together. Lead-2 nitrate, PbNO3 in parentheses, subscript 2, potassium iodide, Ki. They're going to switch partners and form a double replacement reaction. PbI2 will be one product. That is a solid. Remember from the rules that you have memorized, the halogens, iodine in this case, are aqueous with everything except lead 2+, silver, and mercury. So in this case, with lead 2+, it would be a solid. Potassium nitrate, potassium is aqueous with anything, nitrate is aqueous with anything. That's why both of our reactants were also aqueous. This is known as the molecular equation. This is the equation you are most used to writing. This equation shows all the aqueous and solid components as molecular formulas, as our typical formulas. But this doesn't give us a really good description of what's actually taking place in the solution. We know that those aqueous compounds dissociate. So we have another type of reaction that we commonly write. In this case, we're looking at what's happening on an atomic level. We know that all of those aqueous compounds are separating into their individual ions. So we get lead 2+, 2 of the NO3- ions, since there were 2 nitrates bonded to lead, 2 potassium ions, 2 iodine ions in the reactants. The lead and iodine come together to form a solid. They do not dissolve in water, so they stay together as a single compound. The nitrate and potassium stay dissolved. This is known as the complete ionic equation. The complete ionic equation is the equation that shows all of the aqueous solutions as dissociated ions. You have to write the charge of the ion. And the solid compounds do not dissociate and are written as their molecular formula. But you see here that we have a couple of things. We have both potassium and nitrate exactly the same on both sides of the equation. You know from math, when we have a typical equation, if we had something the same on both sides of the equation, we would cancel it out. Well, that's really what we're doing with a net ionic equation. We cross out those ions that are not doing anything in the reaction, that are the spectator ions. Think of the term spectator. When you're a spectator, you generally are just watching the action, you're not actually participating. So a spectator ion is those ions that are not actually participating in the reaction. The potassium and the nitrate we were looking at previously. They're just spectating this. So the real reaction that's actually taking place here is lead 2+ aqueous reacting with 2 iodine aqueous anions to form lead 2 iodide solid. This is known as the net ionic equation. These are the equations that show only the aqueous ions that actually change into a solid precipitate in the final reaction. Or in the case of an acid-base that we'll look at later, those that change into a liquid. If it's changing from aqueous into another form of matter, we will keep them in the reaction. Spectator ions, those that are actually not changing at all in the reaction, are omitted from this equation. So you have 3 equations here. You have the molecular, the complete ionic, and then the net ionic. We want to be able to write all 3 of these for a typical precipitation reaction. So we're going to look through a group of reactions here. I'd like you to try these on your own, and then you can pause the video, press play when you're ready to start again, and see my answer. Okay, nitric acid, we know that is HNO3. It's nitrate, so it's always aqueous. Barium chloride, BaCl2. Chlorine is aqueous with everything other than lead, silver, and mercury. Forms: barium nitrate, and hydrochloric acid. Hydrochloric acid is aqueous. Chlorine is aqueous with everything other than lead, silver, and mercury. Barium nitrate is also aqueous. We need to balance this equation. To balance this equation, we put a 2 here and a 2 here. So this would be our molecular equation. To write our complete ionic, we want to separate these out into individual ions. So we have 2H+, 2NO3-, Ba2+, 2 Cl-. You're noticing now that the subscripts from these previous ones, if they're telling us we have more than one of the ion, become coefficients now in the complete ionic. Forms Ba2+ aqueous, 2NO3- aqueous, 2H+ aqueous, and 2 Cl- aqueous. A good check to make sure you've done this right is to check to see that everything is still balanced. That is our complete ionic equation. Now what you see is that this isn't a precipitation reaction. This is just a standard double replacement reaction. In reality, nothing is really taking place. Everything is staying the same. So there really is no reaction going on here, and there will not be a net ionic equation because everything is a spectator ion and would cancel out. Okay, next, ammonium sulfide and cobalt-2 chloride. Ammonium sulfide, NH4, 2S. We know that's aqueous because of the ammonium. Cobalt-2 chloride, CoCl2. That's aqueous, chlorine with everything other than lead, silver, and mercury. Ammonium chloride is the first product since it's switching partners. We know that's aqueous from ammonium and chlorine. And then cobalt-2 sulfate. The cations keep their same charge on both sides of the equation. So cobalt was 2+ in the reactants, it will be 2+ in the products. Now to understand cobalt sulfide, we would need to look at the rule for sulfur. That's not one of the rules you need to have memorized. If you look up the rule for sulfide, the rule for sulfide is that it's soluble with the alkali metals, ammonium, beryllium, magnesium, calcium, strontium, barium, and radium, but insoluble or not soluble with everything else. So cobalt was not on that list, so cobalt forms a solid with sulfide. Now, we want to write the complete ionic equation. 2NH4+, still aqueous, sulfur 2-, aqueous, cobalt 2+, aqueous, 2 chlorine, aqueous. Oh, we need to balance the equation first. Sorry about that. Caught that mistake. 2NH4+, aqueous, 2 Cl- aqueous, plus COS, solid. So the cobalt-2 sulfide is a solid, so we relieve that as a molecular compound. Now we're going to cancel out anything that's a spectator ion. So we'll have S2- aqueous plus CO2+ aqueous forms COS solid. And that is our net ionic equation. One last example, sulfuric acid and lead-2 nitrate. Sulfuric acid, H2SO4. That's going to be aqueous. If we look at the rule for sulfate, sulfate is only not soluble with calcium, strontium, barium, radium, silver, And lead, that's not one you're expected to have memorized. Lead 2 nitrate, so PbNO3 2, which is also aqueous because of the nitrate. The products will be PbSO4 and hydrogen plus 1, nitrate minus 1, so HNO3. In this case, we know nitric acid is aqueous, has nitrate, so always aqueous. Lead 2 sulfate. We actually have to look at the rules. These would be on your blue sheet in class, or you can look them up in your textbook. You'd find that lead 2 sulfate is a solid. Now balance the equation, make sure it's balanced. So in this case, we need a 2 in front of HNO3. Write the complete ionic equation, 2H plus aqueous, plus SO4 2 minus aqueous, plus Pb2 plus aqueous, plus 2NO3 minus aqueous, forms PbSO4 solid, plus 2H plus aqueous, plus 2NO3 minus aqueous. That's the complete ionic equation. Now we'll cancel out the spectator ions, leaving us with SO4 2 minus aqueous, plus Pb2 plus aqueous, forms PbSO4 solid. So those are some examples of typical net ionic equations. We write the molecular, the complete ionic, and then the net ionic.